Thank you for coming. I am working on a project that I'm calling Nix Native, where I implement per translation unit incremental builds. I use C and C++ as the language for this project, for the language I would build. Calling it Nix Native, I couldn't really decide on the name for a while, but I called it Nix Native because the idea is that your actual build graph is in native Nix as opposed to in some other language, and that you're wrapping some other language that describes your build graph in Nix. And so, kind of the core problem that it's solving is that today, if you want to build something like C and C++, but really any language in Nix, you kind of make one big monolithic derivation. And that's all fine and good. It makes a lot of sense as a package manager, but it's not super great for if you are a developer at your terminal, iterating on your project and you change one C file. If you do a Nix build, it's going to see that input hash, changes, and then it's going to rerun the entire build, and that makes for not quite as fast of an experience when you want to iterate. There are ways around this. So there are things like IFD. That's suboptimal. It makes evaluation very slow. You can't use it everywhere. And you can do impure builds with something like a C cache. That's not great for other reasons. You have to accept the impurity and non-determinism. So what if instead Nix could just understand individual compilation units? What if you did actually just have I think the ideal is that every single translation unit compilation is an individual derivation. So instead of having one big, derivation, I use Slurm for this example. I'll use it more often. It's a kind of a large C project, HPC workload manager that I'm familiar with. I just picked it as a random example of a large C project. But ideally, you would have, one derivation per C to O translation and then one derivation for the link step. And then Nix could farm all of that out and cache at the individual derivation level as it does normally. In order to do this, this doesn't work with kind of vanilla Nix out the box today. You need 3 experimental features, one a little bit more experimental than the others. So you need recursive Nix, you need content address derivations, and you need dynamic derivations. And you can kind of think of this talk as being sort of a marketing pitch for dynamic derivations, which is still out in RFC and still needs to be finalized. And it needs kind of community input at this stage. I'm very much in support of it, and I want to kind of show you what we can really do with proper dynamic derivations. In order to do this, I build on some work from one of my colleagues, Edgar Lee, who's built Nix Ninja, which is kind of really doing all the work here. I'm kind of just adding a nice library layer on top that makes it in my opinion, very ergonomic. But so what happens is that in Nix Native, you just say, I want an executable. You give it a name. You give it the sources, just what source files, you want to compile. We support glob patterns, what libraries to link against. And then what this does is it resolves, the tool chain. It decides if you want, GCC or Clang or what linker you want. It actually goes and, collects the dependencies. And then what I do is Nix Ninja I'll go into in a bit, but I just render a Nix Ninja, a ninja.build file as a Nix templated string, and then I simply pass that to Nix Ninja, and then Nix Ninja does all the hard work. It needs to be content addressed, and it needs to have recursive Nix. And then what Nix Ninja does, Nix Ninja actually does the hard work of scanning the individual C files to find out exactly what header files each C file depends on, and then it creates a derivation for each one of those based on its actual inputs, and then it creates a derivation for the link step at the end, and then it outputs a DRV file at the end. And what dynamic derivations really allows is it adds this built-in output of command. So what happens with dynamic derivations is you create a derivation that returns a derivation, and then when Nix receives a derivation back as the output of a build, it just also realizes that derivation. And so this kind of turns Nix into I've heard John Erickson refer to it as a monadic build system. And Basically, this is kind of the magic of how you actually invoke this, called the drv.drv pattern. You'll see derivations in there that are .drv.drv. Those are dynamic derivations, derivations that return derivations. And so the way I've kind of designed this this Nix library is that at the top level, you have a user API where you can ask for, I want to build an executable, I want to build a static lib, I want to build a shared lib. There's also a project abstraction that kind of bundles default arguments together. I'll show you that later. You can you bring your own compiler, your own linker. There's a policy layer that describes how you want to combine those two, and what you want to do with system link flags. Then you generate the the ninja.build file. You create the wrapper derivation that I showed previously, and then Nix Ninja actually parses the files and returns you a derivation, and then Nix finally builds the final dynamic derivation. So again, you can really compose your toolchain whatever you want. You choose GCC or Clang. You can do any one of the linkers that are available. And what's nice about this is that you have, because the build graph is in Nix, you have all of Nix packages right there. So you don't just have to, it's not in other build systems, they say, oh, I want to call GCC, and then you have to somewhere else, if you have a makefile or something else, you have to somewhere else, you have to say, this is what I mean by, GCC. But in Nix, you have kind of Nix packages right there. You can refer to a very specific, GCC, a very specific Clang, some other compiler that you've written, or fancy. And you have explicit library interfaces. So, for example, you can say I have a static lib. This static lib has a public interface. And then if you pass libcommon down into libcon manager, these are Slurm libraries. The public library, kind of flows through automatically. It also has package config support, so you can, when you want to pull in some LZ4, like some library from Nix packages, like in here I have packages LZ4, which is a compression library that Slurm depends on. You give it this little package config wrapper, and then you can also pass it in as if it was a normal Nix native object itself. So it supports integration with, at the build level with other things in Nix packages. And so I'm going to do a demo in a minute. But so just to explain like what Slurm is and what it normally looks like, it's a fairly large project, large project. There's 10 libraries, 20 CLI tools, 5 daemons, 2 external dependencies, and it generates a 375 line config file. And so LZ4 and Lua are 2 things that come from Nix packages via package config. It creates 3 static libraries. Create some shared libraries, and then at the end it creates various CLI tools and daemons at the bottom. And this is what the build definition looks like, which I think is actually looks fairly nice. You define your sources up here. We support glob patterns, so you can just say all of the C files in this directory, and then this is what a project definition looks like. So you define your project. This kind of just sets default parameters that are inherited by everything later. So when you say slurm.staticlib, it just inherits all the fields that you define in the Slurm project. And then you can create a helper function called make CLI, which similarly bundles several parameters together. And essentially this is sort of what a build definition looks like, which I think is not too scary. And then I'll show you in practice because I have it working. So I will. I have my Zealot here, so I have this synchronized. So if I show you, so I have on the left side I have the Nix native build of Slurm, and on the right side I just took the Nix packages definition, so the standard build definition, and I have it already cached. So if I run it right now, they both take no time at all, basically both instant. And then what I'm going to do, I've been editing a file, so they both, I'm just taking a random string in one of the files and editing it so that it creates a novel file. So I'm going to go do that. So it spits out a lot of garbage, but then it's done in 2.89 seconds because that's kind of all that you would expect it to take to do this. And then on the right side, that's going to keep going for 157 seconds. I've done this enough times. Yeah, and if we turn off sync and we go over here, results, as info, it's not gonna work because it needs to be have a whole configuration on the system that it doesn't have, but it actually runs the the binary. We could wait for this to finish, but it's gonna run for 157 seconds. So this is what your life could be. If you have your project, if dynamic derivations goes in, and you can you rewrite your project to be either just use Nix Ninja directly, or you can write it with Nix Native, and then this could be your iteration cycle. The reason I find this like particularly compelling for Nix in particular is because if you think about what this really gives us, like if you compare it to the other build systems like Bazel and Buck2, like what do they have going for them? They have a per file action graph, they have content address caching, they have hermetic sandboxing, remote execution. They write their, they both have their own respective Starlark DSLs, which is like a Python-like language if you're not familiar. And then they kind of have their own, package ecosystem where people have built other stuff in Bazel and Buck2, but they kind of only work with themselves. If you have dynamic derivations and you use something, like a Nix library to describe your action graph, it doesn't have to be Nix Native, it could be anything built on dynamic derivations. You again have per file derivations, not just called an action graph, but instead derivations. You have again content address cache because we support that. You have the Nix sandbox. You can have, we have Nix remote builders and binary caches. For example, nixbuild.net. So you can farm out and have remote building and remote caching. Use the Nix language, which is a language that everyone in this room is already going to be familiar with, and we already like to use. And then you have all of Nix packages, which is a much, much, much larger package repository than the Bazel or Buck repository. And I think it really ends up being a better solution. If you compare what trying to build this project in Bazel would look like compared to Nix Native, it's really mostly mostly the same. You say I want a library, cool, I want a library, I want a binary, I want a binary. Bazel has a way to fetch remote repositories, but remote things that are not already in Bazel and build them. But it's kind of clunky. It's Nix packages is just right there. It's kind of what we've designed Nix packages to do. And so again, you have all of Nix packages in scope, and you can mix and match your toolchain however you want. Compared to I don't know if anyone's ever managed tool chains in Bazel or Buck2, but it's kind of the most painful part of it. In Nix, again, you just referred to what symbols you would like. And then we also have, dev shells out the box. So I think between, Nix packages and dev shells, this capability puts us at a feature complete, level with Bazel and Buck2. But then because Nix has all the other advantages, it results in a much better overall experience. And it makes it a much more powerful tool. I described this to, John Erickson a while ago, who's the one pushing forward dynamic derivations, and he said that Bazel and Buck2 are fast first and correct second, but in Nix we are correct first, and now we just need to make it fast. So it shouldn't be surprising that we can do this because we've done kind of the hard work. We have the correct design out front. We just kind of need to make this last layer. And again, every C to O gets its own derivation. You change one C file, only that rebuilds. We have shared binary caches, so two different developers that are working, on the same project. If they want to compile the same project, think about how many compilations are the exact same compilation over and over again. Never again if you have the derivation at the individual translation unit level. People can be working on different branches, and if they're just compiling the same file because you only modify, one or two, a couple files per branch, then those get deduplicated. So it can really massively turbocharge the amount of reuse we get in practice. And then just other things that I support. You can mix C and C++, so you can compile a C library and a C++ library, and then link it to the C library. Currently the way it works, it auto detects based on the extension, and auto selects which compiler to use. You can easily use PyBind 11 to make Python extensions. You have transitive library change. So if this library depends on this library, depends on this library, and you pass it through, it automatically gets the other ones. I have it, I have C++ linking against a Rust library, so I compiled something in Rust, using build Rust package. Later, I can, I have some work in progress to do the same kind of incremental builds against Rust. I use C and C++ for this project. But, if you build a build Rust package, then you can, link, a C++ thing against it very easily, very ergonomically. yeah, you can use you can have other I have this other tools abstraction where you can do Jinja and other kind of code generation um, things, which I use autocomp in the Slurm example. So yeah, that's it. That's all I have. If other people are interested in pushing this forward as a direction for Nix to go, please reach out. And that's all I have.